All right, so here we go again. Basically, I've been given this talk or some form of this talk year after year after year, and I think this holds through. If we look globally this past year, depending on whether you look at NOAA or NASA records, we're talking about either the third or the second warmest year on record in advance. All right, so the obligatory what are things doing? I'm going to breeze through these. Obviously, in the northeastern United States, if we look at things like annual average temperature over the last 100 plus years, there's a pretty good upward trend, particularly since the 70s. You can move on. If we look at things like rainfall, I guess we can debate whether this is going up or down. I guess on the aggregate, probably a small increase in average annual rainfall. If you go on. In kind of keeping with Randy, if we looked at drought, probably not much we can say about drought in the Northeast. If anything, we've been pretty lucky, except for 2006, which isn't on this slide in terms of drought. You can go on. All right, so if I pull some from some graphs that actually came out of the last National Climate Assessment, actually a neat number of kind of state reports for each of the states in the Northeast, each of the states in the country. Guess I picked on my new favorite home state, New York, being up at Cornell. What we see is a lot of this change in temperatures occurring during the winter season. Don't go outside, and maybe that'll make sense. If we go on, summer temperatures, yeah, a little bit warming there, at least in the historical period of time, but not as much as we see in winter. That's going to change in the future. You can go on again. If we look at things like the frost-free season, actually a pretty good trend in the period of time between when we see the last below freezing temperature in the spring and the first in the fall. You can go on one more time. And again, don't look outside, but days with snow cover, particularly in New York and the northern part of the region, have shown a dramatic decline. So this is the number of days that the snow actually stays on the ground. Has nothing to do with snowfall, so you can, don't have to look at the news and all the nor'easters. But even here, if you look outside now, a number of substantial snows over the last couple of weeks, but yet pretty much clear ground. And I would say that's the same across the region. Go ahead. Very cold nights, moving to Pennsylvania, a dramatic decrease in these. I thought the line was on. I guess not. In these very cold nights occurring in the wintertime. And go on one more time. But a lot of times what we hear is the summer days are going to get much hotter. But if I look at the observational record for Pennsylvania, New Jersey, any place in the Northeast, we really don't see this yet. Go ahead. Extreme precipitation. Again, Randy mentioned flooding in the field and things like that. Thank you. Ooh, now you can hear me? Put that down. This has been one of the biggest changes that we've seen, these big, heavy rainfall producing events, 1, 2, 3, 4 inches in some places. And again, it's going to have profound effect, I think, on agriculture. One more time. You can go ahead. All right, so what does the future hold? And I'm going skiing in Lake Placid this weekend, hopefully not on grass, but go ahead. Again, just to set the stage, I'm sure you've all seen this before. Basically, this is how carbon dioxide in the atmosphere is expected to go. We're kind of there where the pink arrow says, just above 408 parts per million. I guess I changed this slide in the class that I teach at Cornell, probably for I've been teaching the class for probably 15 years, probably for the 15th slide, because every spring that number goes up. I think it's at 408 right now, if I remember correctly. And really, most of the slides that I'm going to talk about are on that pathway, the red pathway, which now is called an RPC 8.5 pathway. It's kind of if we keep on doing what we're doing now, keep on emitting fossil fuels, greenhouse gases at the current rate. Maybe in some of them you'll see that lighter blue line. That's RPC 4.5. That's where it would be nice to get, but still is probably not enough to get to that point. Go ahead. All right, so as Dave said, where I'm going to pull kind of the rest of these slides from is the papers that I worked on with Dave and Alex. And again, kind of a show of what it's like in the world today. Wrote this paper with Alex, and this morning was the first time I actually met Alex in person. So kind of interesting there. Anyway, so working with Alex, really, again, where I'm going to go now is, instead of these broad, the temperature's going to go up, the rainfall's going to go up, is really starting to get at, where does this matter? Where does this matter for agriculture? And then also in the next couple of slides is kind of saying, all right, let's not put our blinders on, but realize the ag systems and things like that are multifaceted. So, maybe just an increase in temperature, we might expect that alone to have some effect, but when we bring everything together, there might be some surprises there. So, again, with the livestock, what we looked at is a number of places around the Northeast. You can see that in my legend. And this is days above 85, I guess 29.4 degrees C for the scientists in the room. And this is a threshold where dairy production, milk production in cows really starts to tank. Okay, so if we look at this figure based on both historical data from the 80s and then projected data going out into the future, we see that this number goes up. And I'm sure you'll hear from Alex in a little bit exactly what this means for the cows and particularly for milk production in a good part of the Northeast. You can go on, Mike. Again, so I'm not going to have this idea of a holistic view of the growing season. And I'll put in a shameless plug for my center at Cornell. These are some graphics, online graphics, very interactive graphics that you can access on a website called the New York State Climate Change Science Clearinghouse. And what's neat is not only does it show New York, but it also shows the neighboring states. So I do have New Jersey up there. And basically what I have here is annual growing degree day accumulation for New Jersey over a historical period of record and then into the future. And basically the idea is actually all of this data, except for the dots, is model generated data. So this is the latest kind of series of downscaled climate model data. It's like an average of like 30 different models. And they simulate the historical period, and they also project into the future. And kind of that range from the red to the blue is actually the range of the models. There's 30 models. The top red line is the warmest of the models. The bottom blue line is the coldest of the models. And the kind of gray line in the middle is a weighted mean of the models. Okay? These are all the same greenhouse gas scenario. So it kind of gives you an idea of the uncertainty in just the projections. But I don't think you'll argue with me either in New Jersey or Vermont up at the top or New York down at the bottom. Growing degree days increase substantially through time. And if you can see my numbers, basically, if you want to go all the way out to the end of the century, we're basically looking almost a doubling of the number of growing degree days that we would expect in a typical growing season. And even maybe more in mid-century, collecting 500 or even 1,000 more degree days. You can go on. Okay, that's one part of the growing season, how much heat accumulates. When does the growing season start? So here I've picked on the last 32 degree Fahrenheit temperature of winter. Again, in New Jersey, typically early on, I guess I'm looking at these are the days in May with below freezing temperature. So you can see even here in New Jersey, on average in the historical period, there are 1 or 2. That's good because I think Rutgers taught me not to plant my tomatoes until about Mother's Day. So that kind of corresponds with this data. Come on, you guys are a tough crowd. I get more laughs out of my class at this time of the morning. Come on. And like we can see through time in all of these cases, essentially as we get out almost to mid-century, it doesn't freeze anymore in May. So I can plant my tomatoes on Easter or sometime in April. So go ahead again. And we can kind of see, again, in a map view for the Northeast, if I look mid-century up at the top, the change in both that freezing temperature in the spring and in the fall over there, if I look at the color bar, about 10 days. So it's getting 10 days longer on both ends, 20 days. And if I go out to the end of the century, lots of red across the region, 25 days, almost a month longer on each season. So a big change there. It's like, wow, great. I give talks with Dave Wolf, and he's, watermelons in New York, peaches in New York because of this. But I think you can go on if I remember my slides correctly. It doesn't necessarily mean that. You can hit it again, and hopefully you can hit it again. Next slide. And that's my animation. That was my joke, and he messed it up. All right? What I wanted to say was stop. Wait, no, maybe this is for anybody that's my age or older, Mr. Magoo, the most famous Rutgers alumni that I could find, and Mr. Magoo was nearsighted. So he didn't, it's like, so maybe we're being nearsighted here to say this growing season might be, we can plant these different crops. Now you can go on. So this is some work we did in our paper in climatic change, and what we see here, kind of a complicated graph, but the black line is that decrease in the date of the last spring freeze, so that's going down. Got to look at the axis over here on your right, starting off at May 1st and ending up on April 1st. And the green lines are the amount of rain that falls in the 3 weeks prior to that date. So it's kind of a moving target, okay? And that red line is kind of the average there of that rainfall. And what we see is early in the record, it's great. It's the last day in May, and actually precip is pretty low, so I can get out into my fields and plant my crops, and everything's doing good. But as I move through time, and this date moves to April 1st, what I see is during that time, again, just natural climatologically, that's the wetter time of year, and also with climate change, we see that's the time of year that rainfall increases the most. Okay, so maybe looking at the start of the growing season as being a frost problem isn't the thing we should be really looking at, but I think you can go on. It really might be, can I get into the field and work? Okay, you can go on. Another thing with apples, okay? So one of the things I started off hearing is, boy, we got to change to different varieties because we're not going to meet our chilling requirements for apples. Okay, and basically what this shows is up at the top, that's Ithaca or someplace near home for me. And if you look at the lines, whether I increase or decrease the temperature, even if I increase the temperature in winter by 5 degrees, I'm good. I have to get to that level of about 1200 there, and that's actually a high chill level, and I make it regardless of what I do. Down in the bottom, that's like, I think it's the apple growing region of North Carolina. Okay, there I have a problem. If I warm it too much, I barely make that line. So lots of years that I don't get my chill for apples. You can go on. I also look at the phenology. All right, in any of these cases, any of these phenological stages in apple, down through time, earlier. Go on. So what does this mean for frost risk? And again, the idea here that it might be more than we think about. So this is simulated data. It's basically a statistical representation, of the climate, the temperature climatology. But what I can do is, if you notice, the bottom axis is a change in temperature, and the upper axis is a change in the variance of temperature. Okay? So basically, how warm is it in aggregate, and how quickly does it change? What I see at the top, again, Ithaca or the apple growing region of upstate New York, no matter how I change, and the numbers and the lines on the graph in black are the probability of getting a freeze event, a damaging freeze event. So if you notice, if I change the temperature 1 degree, 2 degree, 3 degree, 4 degree, 5 degree, I parallel that line. So my risk of frost does not change very much in upstate New York as I warm the climate. But if I change the variance by even a little bit, 5 or 10%, I have a big change in the risk of frost. So really, spring frost is not a temperature average phenomena, it's a variance phenomena. If I go to the other side, North Carolina, it's very different. If I go across this graph now and change the temperature, I have a big change and actually a reduction in frost risk there. Frost is much more common there or frost damage is much more common there than in upstate New York. 5, okay, go ahead. So if we look at some stages, and particularly the early stages of development, silver tip in black, green tip in purple, and even up to tight cluster in yellow, through time, whether I'm in the historical period or out into the future, the risk of getting an LT10 event, 10% of the blossoms killed, again, not a lot of blossoms, goes down with a changing climate, with a warming climate. I've warmed it in each of these cases, and I am forgetting that's the average, how the average temperature actually changes in the model in that case. But if I start to look at the later stages, anywhere from first pink to petal fall, I see a different pattern. And actually I see a short-term increase in risk. And again, these data are for upstate New York, so a climate like upstate New York, pretty much the same as like Vermont or something like that as well. And then it's not until mid-century, up until mid-century, I see a peak. And then as time goes on, I start to see a decline. So again, a very different thinking. Maybe a short-term problem, perhaps not a long-term problem. Again, looking at it a little bit deeper. The other thing is like just fungal diseases in plants. I work a lot with turfgrass with Frank Rossi at Rutgers, and actually Rich Buckley here at Rutgers as well. So this is dollar spot, and our model of dollar spot shows an increase in the prevalence of this disease through time. But however, I look at something like relative humidity being a surrogate for leaf wetness in this case, what I see is a lot of brown in this map in the future, saying that the prevalence of relative humidities on average in the morning will be lower. And therefore, again, even though we don't have direct projections of leaf wetness might go down. So, what's going to happen there? Well, how about precip? That might be another issue too. Spring and summer precip actually changes very little. So in the end, we're just starting to get into this, like prevalence of disease. That's an idea of something we really have to look at a lot deeper to say, are we going to be putting down more pesticides or fungicides, particularly in the Northeast? So to kind of end, basically we need to rethink the way we do things. We've been so ingrained in kind of using climate to make these decisions, and we might not even know we're using climate to make a lot of on-farm decisions. We use averages for things like degree days and frost days. Typically use a 30-year average. Why? Because some climatologist 60 years ago decided 30 years was a good number to use. It assumed the climate was stationary. It had no trend. Okay? What recent research shows is maybe a 15-year record is a better way to do it. You don't have all of those, those 15 years way in the past that have no real relevance to what we have today. So in making our recommendations, maybe using a shorter climate record is the better prediction for the future. We can also throw away the calendar. I said maybe Mother's Day to plant tomatoes isn't the thing to do. And we should also throw away intuition, all right? Our intuition is basically based on the past climate. We've done it for this many years. We've done it this way. We need to replace this with data. So this is a segue for my colleagues the rest of the afternoon. We have to make use of these mesonets that are out there, run by Dave here in New Jersey and Kevin in Delaware, and my colleagues at Cornell actually, and across the Northeast in New England with NUA. We need to put these into models so that farmers and even home gardeners can really start to make informed decisions based on the data. When should I plant, or when should I spray for specific diseases? When do I need to water or irrigate? So a call out to the group at Cornell up there for the KICS tool there for the water deficit calculator, and my colleagues at NUA in New York, and Glenn and the rest of the group that are even in New Jersey that are participating in the NUA project. So about time. I guess I've kept you off track for this morning, so I don't know if you want to entertain questions or at the end.
So I look at the trend for the degree days, and I'm thinking, correct me if I'm wrong, I'm the director of extension here at Rutgers, I need to hire more IPM scouts is what I'm guessing. If the degree days are going up, we're going to deal with more pest problems. Is that a fair assumption?
I know the dean's here, so I'm going to not say no, you don't need to hire more. So, yeah, and I think two things. Yes, you should hire more, but I think they also have to be smarter, and I don't mean like go to Cornell versus someplace else, but smarter from the fact they have to use these data. So you don't want them to start going out like now in a year like this because Art said, the springs are going to be getting earlier. That's not the case in this year. So by using like the New Jersey Mesonet data in these tools, you should basically be saying, all right, now we're reaching this peak period. You should be going out and scouting like crazy and now because this is when we're going to see it. That make sense?
You mentioned about the difference between 30-year model versus 15-year models. So have you looked at even shorter periods, 5-10 years to see if that's a better fit?
Yeah. So that's some research that a colleague did, and the idea was this: is what averaging period was the best predictor for, I don't remember if it was the next year or the next couple of years. And in that case, 15 years won out. So they looked at a range of different averaging periods, and 15 years tended to be the best thing to predict the next year. I think with precipitation, it's actually 10. It's a different number for temperature versus precip. So the answer is yes, and I think that was in the Journal of Climate or the Journal of Climate and Applied Meteorology.
What suggestions do you have for how to communicate this idea of throwing the calendar away and denying one's intuition when that is how many, not just agricultural, but any kind of decisions are made by humans?
Yeah, that's been tough. I think Randy hit on it in her talk that, it's really going out and communicating with the farmers and showing them, that there is economically or whatever kind of a better way to think about this. Kind of the proof is in the pudding, and that's really what you have to show. So I think by doing the retrospective analyses and getting them on board, it's been tough even with like a lot of the spray tools and things like that with NUA. But once you get a set of farmers, a set of growers that start using it, then they become your advocates, and then it kind of starts to snowball there. And I don't think we're quite there yet. We're kind of right on the cusp.
So you did us proud, Art. Thank you. So
thank you.
There are a couple of things that you haven't taken account of, and I just want to probe to see how you might think about it. One is, of course, genetics. Things are slow in modifying apples, but annuals, of course, the climate issues are going to be folded deeply into genetic improvement programs. And the other one about intuition, which probably changes as slowly or slower than tree breeding, but intuition does change over generations at least. And that begs the whole question of what we know from cognitive sciences and how people learn and how people adjust to the global issues that they face in their daily lives or whatever. Just how are you thinking about the ecumenical needs of sciences across the social sciences as well as the physical?
I'm going to bag out of the genetics question because I'll admit that was the hardest course I took here at Cornell. So at Rutgers over in Blake Hall. The intuition question, and I think that's really where kind of I want to say, yeah, it is. It's clearly a social science, psychology, and things like that, because it's kind of twofold. It's not only, yes, we've done this for so many years, but it's also a thing I see, it's cold this winter. So memory is also, you have that long-term intuition, but you also have a very short-term, it was like this last year or the year before, therefore I'm going to do this. And I've been struggling with that. That's probably the area I work most with colleagues at Cornell in that. And the only way I can, the way we're going is kind of these simulations, these case studies and things like that. That's been a tough nut to crack.
All right, well, thank you, Art. So.